as low as is possible in our case. But how to reduce the input size? Because inputs are basically my features. So what is happening in the first two cases here? Whatever data set you are taking, you may take disease detection data set, you may take a image processing data set, or you may take a speech processing data set. Suppose this is my data set which I'm taking, okay? And in that specific field, some features are going to be extracted. So these are my features, okay? And these features are going to be effectively combined here and given it to a small classifier. It can be a KNN classifier, it can be a neural network based classifier, it can be SBM, it can be random forest, whatever. Then a normal classifier, all of us know. After that, we are going to find out the accuracy of the algorithm. It may be classification accuracy, it may be precision, recall, different type of classification measures are there. And while performing all these equations, we are going to run this whole set for multiple number of times with the features. Means these which features to be selected will be decided by this feature selection block. So it is having two components. Okay, one component is our the normal neural network, which is going to take the inputs, give you the output in the form of the classification accuracy or in the form of the low error rate. And the second block which I'm using is called as the feature selector block. And the PSO is working in the second block, not in the first block. First block is going on as it is. What actually PSO is helping us is selecting the best possible features. Means we can do this thing manually. Here, as I've told you, we can do this selection manually. Manually means I'm going to take this one feature, feature number one, combine it with multiple number of other features, and I can check. Second feature, and I can check. But if I'm going to check this thing individually or in the manual level, then there are a lot of complexities will be there, as well as the lot of time will be wasted. And also I cannot guarantee that whatever the result we have got is proper or not, the result I have got is correct or not. So for to solve this by using a simple optimization algorithm is the best option for us. So let me take one example for today. So what I've taken, that one popular dataset I have used, that is called as the ionosphere dataset. Okay, in this ionosphere dataset, we are having some 34 features. Okay, and there are some outputs. And what I'm doing, that this ionosphere, I'm giving it this data set, I'm giving it to the KNN classifier. And this KNN classifier is going to give me certain output or certain classification accuracy. And have you heard these terms like k-fold cross validation, like the precision, like recall? These terms, I think you may have heard little bit in your ML thing, like SBM classifier, how we do the classification accuracy. Is this being little bit covered, or should I cover it in the class, in the total? It will take 2-3 classes to cover. Yes, yes, covered.
Yes, sir.
Okay, okay. So even if it is covered, still I'll take one class to just discuss what is a ROC plot, what is basically the our precision recall F1 score, F2 score. It will take 40-50 minutes to cover. That I will do in one class in next week to have a clear idea how our classifiers are going to be evaluated. Now, suppose this evaluation parameter you know, and we are giving one, giving this data set and getting this output. Okay. Now, what this and the objective function is, suppose the output is error means classification accuracy. Whatever the classification accuracy, maximum classification accuracy can be 100, or I can take it as 1. So if I am going to do 1 minus classification accuracy, that thing I can call it as my error. So I want to reduce the error. Or if you want to take it as a maximization problem, this thing, if you want to do it as a maximization problem, then you can take your objective function as classification accuracy should be as high as possible. If you want to take it as a minimization, you will write 1 minus classification accuracy, or maximization, classification accuracy should be more. And each time my PSO is going to take one feature and do the calculation. Second feature, do the calculation. Third feature, do the calculation. Let's see how this thing is working. So for this thing, I'm taking one small paper, just a 4 5 year old paper. That link again I'm going to share today after the class. This has been implemented in Python and C also. So for my convenience, I am taking the MATLAB and I am showing you. So see, this is the first. I think it is visible. Let me increase the size a little bit. Okay. So first, what I'm doing that I'm just erasing all the data which is present on the workspace. Now, in this is one simple data set which is available that is called ionosphere data set, and that data set I have just uploaded into my system. So in here you can find that this data set dimension is basically 351 into 34. Just look here, the data set which I have uploaded here. This is 351 into 34. So what is this 351 into 34? Is that there are total 351 number of samples. So please understand this. If you can able to read what exactly present in the data set and what is the dimension, then our job will be very easy. So you see, this whole Excel sheet or whole this CSV file is having 351 number of rows. So 351 number of samples are there. And uh, each sample is having total 34 features. Similar to our gate circuits, which we have used in designing the neural network. So if I'm talking about a simple gate here, if you think of simple gate, okay. Suppose I want to implement XOR gate. So how many number of samples? Four number of samples. That is 00, 01, 10, 11, and there is one output. Output will be there 0110. So here the number of samples are 4 and the number of features are 2. So this is a 4 by 2 its size. And whatever I am taking now is basically 351 into 34. That is the our data set which I have used. This ionosphere data set is available in all the language platforms. Now suppose this thing is clear, that what is the data set. Now the challenge is that out of these 34 features which are used in this data set, I want to reduce this features. Means out of this 34, I don't want to take all the features, because you see in one case the values are only 111 000, so which are not required for our calculation. Those features I can easily omit. So let us see, let us go to run the algorithm. Now here what I'm doing, I'm setting out that what is the held out test or what is the hold out method. So the hold out method means whenever we use any data set for training and testing in our ML or AI platform, we take 80% of the data for training and 20% of the data for testing. So this 0.2 means how much amount of data you are keeping for your validation or for your testing. 80% is going for your training, 20% is going for your testing. Now here it is going to just dividing the data, this 351 data, 351 samples into different, let me run it again, you will understand. So if I'm running it here, you can see that it has found out from this 351, 281 it has taken as my training, and 70 it has kept it as for testing, and the total number of observation or total number of samples are basically 351. So 80-20 division has happened. After that, if I'm going to proceed further here, now these are the parameters which are used in PSO. PSO means it is asking for you that how many particles or how many birds you want to use for your searching. If you can recall, in PSO, whatever the searching we is going to happen, we are going to assign some of the agents for do the searching. Okay, as I have told you here. that instead of one person doing all the calculation, what is the main goal is that uh, once from this side, the board number one is going to do the searching. From this side, the board number two is going to do the searching, and arbitrarily, the board number three is going to do the searching. And as well as they are going to interconnect with each other. That what is the result at your side? What is the minimum objective function you are getting, or what is the classification accuracy you are getting? Like this, after intercommunicating, slowly they are going to move into the global best or to the optimum value for your calculation. Similarly here, I have selected 10 number of agents. Okay. And this C1, C2, W are basically three constants which are used in this PSO. So we'll discuss detail into this constants. So basically these are the constants. These are the PSO equation which you've discussed in the class. If you have forgotten, that's okay. Means this is a main equation, that this is one solution, first solution, this xt, this is the next solution, xt plus 1. How it will be calculated? By adding a velocity. The velocity is going to be calculated from here, or the change in the or the new position will be calculated by three parameters. One is called the inertia, second one is called as the personal component, the third one is called as the social component. So this w C1 and C2 are constants. These I can change as my wish. So C1, C2 are basically selected for the movement. R1 and R2 are the random parameters. So let's go back. These values you can change. These are not fixed. I've taken 2 to 1. You can take of your choice. Now, going to implement this PSO. PSO has been implemented as a simple function, and it is written as JPSO. Let's go to JPSO and see what it is. So JPSO is this. Okay. So now it is going here. Okay. It is asking what is the fitness function, or what is the objective of this whole calculation. So the fitness function has been mentioned here. Okay. The fitness function is saying that you take the features one after another, okay, and give it to a KNN classifier. Okay. And at the end, you try to calculate what is the accuracy. You select arbitrarily one number of features and find out what is the classification accuracy you are getting. So after finding the classification accuracy, you calculate the error. That is the objective function. Again, let's go back to PSO. Here it is asking what is the size of the dimension. The size will be this 2. After that, we are taking the values for this calculation, like this x and v and y. So this whole equations which has been written, this equation velocity update C1, C2, R1, R2. So these things are basically our PSO equations. Let me run this whole code once, then you will understand what benefit we have got. Okay, let me run it once. Okay. So see on below, you can find out that it is running for 100 times, because I have given the iteration to be 100 below. Okay. And now you see that it is giving me that initially, please look into the right hand side. Initially, the number of features are there as 34. This number of features are basically 34. Now it is saying that out of this 34, it has selected 10 number of features. It has selected 10 number of features. Okay. And by using the 10 number of features, means now my whole this data set has been reduced to 10 number of features. And by using this 10 number of feature, you just look below what is mentioned, that it is saying that the time of calculation had reduced to 50%. You can see the previous calculation when I have taken the total features is 0.4 seconds. But if I am taking the reduced amount of features, it is becoming 0.23. This is one advantage we have got. And also the accuracy is not been much been compromised. It has been previously 0.86. Now also the accuracy is around 0.85. But the main benefit I have got that the time has been reduced. No. Uh, are you getting my point what I'm telling? That now the whole feature, one subset I have taken, and that subset I have started the calculation. And by taking this subset, I found out that the whole time which has been taken for the 34 features has now been reduced to total 10 number of features. And by doing so, the time required for whole calculation has been reduced to great extent. Almost 50% my time has been reduced. And how much drop in the classification accuracy? So hardly 1% drop is there. So this I can use for my real-time implementation. So again, I'm running it for next validation. So now you see for the second time, if I'm taking, again, it is doing this whole calculation. And at the end, after 100 iteration, it is going to select the features. And these features are going to be this. You can see here, see at this point. The features which are being taken as now 6 features I have taken. So in this way, the whole calculation we are doing, or by using this PSO, I'm reducing the. Okay, you are saying the attendance is not accepting. Just 1 minute. Okay. So I think now the attendance link is active. You can check. Just let me check. And I'm just sharing you this whole code and this paper. Okay, and you find out that how this algorithm is working. And mm, any update? Have you searched any data set for this thing IPL prediction and all? Have you searched anything? No. Okay, fine. If the searching,
Yes, sir.
Yes,
okay,
sir.
fine. Even if you are not able to find correct data set of IPL, you can take any data set where the input feature size is more, okay? And try to select some of the features by using this PSO and try to see that by using it, is there any reduction in time or is there any reduction in the computational complexity or is there any reduction in classification accuracy? These things we have to try and then we can understand it properly. So I am sharing you this code as well as this paper which has been used for this implementation. You just try it once and then ask me the doubts by Monday class. Okay. So in the first go, you may not understand it properly, but slowly, when you'll run this whole algorithm for multiple number of time, then your concepts will be clear. At least now, are you able to, whatever the work PSO is doing, that you are able to understand or not? Means why we need this algorithm. How the algorithm is working, that thing is different. But if I'm using this PSO, the benefit what I'm getting is instead of one person working, multiple number of agents are working for me. And they're communicating with each other. And after this communication, they're giving me the best solution. Okay. Or this is the whole concept of swarm intelligence, this thing. And they're using these two equations to finally update their values. So in the subsequent classes, I'm going to take multiple number of problems and this PSO code also, I'm going to write it line by line so that you can get a clear idea that how this communication is happening. Okay. How they are going for the current direction, the personal based direction, the global based direction, and how one after another they're moving. And this thing is converging into this three equation, this equation, the velocity or the next location for tomorrow, how we are calculating the next location for today, how this whole calculation is happening. And one more optimization technique also I'm going to discuss maybe by next week. And two algorithms you can compare one after another for the same problem, then the idea will be clear. So by end of today's class, I'm going to share you multiple number of papers which are based on this feature reduction. And by using swarm intelligence, you just run it in Python, in Java and all, just see what is happening. Okay, so this much for today. You just run it in your place, or if you want, you can come to the ECA department. There is a lab also. You can run it here. But running simulation is more important. Otherwise, this concept you cannot understand properly. Okay. So anything, any doubt, if you want to put in, you can put in here. No. So if there is no doubt, let me end the class here, and we are going to meet tomorrow. We'll see online or offline. I will inform by today because some strike is going on. Let us see what is happening. So accordingly, I'm going to inform. So that's it for today.
Thank you,
Thank
sir.
you, sir.
Thank you, sir.
Recording stopped.